Good morning, ladies and gentlemen. So today I wanted to go over the entirety of problem 1 from the Calc Review 9 video. And then I will sort of look through the questions asked and deem if it's necessary to do a video on the second problem on this same worksheet. So I'm going to go through this in decent detail. I've already worked out the problem, so I'm not going to spend time writing out the answers. You can read the answers. I'm also going to sort of do a little mini lesson on concavity because there seems to be a lot of confusion regarding concavity. So anyway, let's get to it. So what I've done is I've filled in the area under these curves just because it's going to be required. And I noticed that I used all positive numbers here. Now, area under a curve when we're referring to integration could be positive or negative, and that depends on a couple of things. What is the direction of integration? So is our d of x positive or negative? And is the curve under the x-axis or is it over the x-axis? So is the height of our curve positive or negative? And remember, when we're integrating, think of that as an act of sort of adding up the areas of many rectangles. And rectangles will have positive areas if their heights and widths are both positive. A rectangle will have a negative area if the height is positive but the width is negative. And so I'm sort of like drawing these arrows in the direction of the delta x. All right. And of course, and I guess I'll draw these arrows in the direction of the heights. And of course, if our delta x is positive, but our heights are negative, then there would be an overall negative area of our rectangle. And if our delta x is negative and our heights are also negative, then there would be an overall positive area. So we have positive area, negative, negative, positive. So we have to pay attention to these things when we are integrating. All right, so we'll keep that in mind, and let's just go ahead and read through this problem. So we have a continuous function f. This function is defined on the interval from -4 to 3 inclusive. And we are told that these shapes are 2 quarter circles and a line segment. Okay, and then they define a function g of x, which is related to f of x, and there's also a 2x term. All right, so really these questions focus mainly on g. All right, but g of x is defined for us. It's right there. So question 1 says, find g of -3, then it says find g prime of x and evaluate g prime of -3. All right, g of -3 is simple. Just plug in -3 into our defined g of x function wherever we see x. So this becomes 2 times -3 plus the integral from 0 to -3. See, I plugged this in and I plugged this in. And now all I have to do is, okay, well, 2 times -3 is -6, great. Now I have to worry about integrating this guy right here. Well, that is just the area under the curve from 0 to -3. Notice we have positive heights and negative dx, which means that our definite integral overall is going to be a negative number, which is why instead of positive 9 pi over 4, I wrote my answer as negative 9 pi over 4. All right, and so that sum is the answer for that first part of part A. All right, g prime of x. So I kind of did this in 2 parts. First, well, the derivative of 2x is, with respect to x, is just 2. So that's kind of simple. Now we need to know the derivative of the integral from 0 to x of f of t dt. Well, what I did first is I wrote out what the fundamental theorem of calculus says the integral from 0 to x of f of t dt is. And so this is what that definite integral looks like if I were to evaluate it by hand. It is the antiderivative of f evaluated at x minus the antiderivative of f evaluated at 0. But now I'm differentiating that. So this d dx applies to both of these terms. Well, the derivative of big F is just f, and the derivative of big F of 0, so actually, let me start that over. The derivative of big F of x is just f of x, little f of x. The derivative of big F of 0 is just 0, because big F of 0 is a constant. So the derivative of a constant will give me 0. My derivative function g prime of x is 2 plus f of x. And now when I evaluate g prime of -3, it's just, again, as simple as just plugging in numbers. So wherever I see an x, I'm going to plug in a -3, and there we have it. F of -3, well, how do I determine that value? We are given the graph of f. So I go up to the graph, I check out where x is -3, which is right over here, and I take that y value. That y value happens to be 0. All right, so that's why this is a 0. And g prime of -3 is 0. Okay, on to part B. Determine the x coordinate of the point at which g has an absolute maximum on the interval -4 to 3 inclusive, and justify your answer. So the justification is just going to be sort of the work that I am about to show you, but I underline a couple of important things: the term absolute maximum, and also the fact that we have a closed interval. All right, folks, I mean, I've repeated this over and over and over and over again. Whenever you see a closed interval and when you're being asked for an absolute maximum, this calls for a table of values, and you need to evaluate the function that you're trying to maximize at the candidates. So the only possible candidates for the absolute maximum value of a function are the endpoints and the critical points. All right, so absolute max, find all candidates, endpoints, and critical points. So that's what I'm trying to do now. I've already filled out the right side, but so ignore this for a moment. This is my first step. The first thing I did was I filled in my first two candidates, which are my endpoints, but then I had to go ahead and determine my critical points, because those are also possible candidates. Critical points, of course, are when g prime of x is, or when the derivative of whatever function you're trying to maximize or minimize is equal to 0 or undefined. So first I started out, well, when is g prime of x equal to 0? Well, first of all, g prime of x, you might recall, is equal to 2 plus f of x. So I just simply set that equal to 0. That is the same thing as saying, when is f of x equal to -2? All right, well, I go up here and I look at f of x equals -2, and it looks like right around here. So the only tricky part is determining this this x coordinate. It happens to be 5/2. So this is 5/2 comma -2. The way you can do that, ladies and gentlemen, is to sort of determine the equation of this line segment and plug in given information, which is the y value, in order to determine the x coordinate. I'll leave that to you to figure out, because I know you can do it. So anyway, I've determined that x equals 5/2 is a critical point, so that goes to my list of candidates. And g prime cannot be undefined. I mean, if you look at the function of g prime 2, well, that's going to be defined at all values of x. F of x is, we're already told it's differentiable. Continuous. We're told that it's continuous, which means that f of x is defined at all values from -4 to 3. So g prime of x cannot be undefined. All right, we're not done yet. We've just found our candidates. Now we need to actually evaluate G at these values to determine when G is a maximum. All right, so G of -4. This is just like a similar exercise to the very first problem over here. I just take these x coordinates and plug them into my function, and I do have to, evaluate integrals, which is to say I need to calculate areas under the curves. And of course, you do need to be careful about whether those values are positive or negative. So anyway, without going through the work, because I think you can calculate and add areas on your own, G of -4 ends up being -8 minus 8 pi over 4. G of 5/2 equals ends up being 5.75, and G of 3 ends up being 6. So we would finish up by saying the absolute maximum of G of x occurs at x equals 3. And why did I list where it occurs? Because that's what it says. Determine the x coordinate of the point at which G has an absolute maximum. Right? They're not looking for the absolute maximum value. They're looking for the x coordinate at which the absolute value occurs. Okay, part C. So this is the one that I saw a lot of questions being asked. And also, I think there was another concavity question on the second problem, and there were a lot of questions being asked there. So I wanted to sort of just do a little quick mini lesson here about concavity. So concavity, there are two, I guess, possible concavities that your graph can have: concave up or concave down. So concave up means there's a portion of curve where the derivative values are increasing. Meaning, if we take a portion of curve that's concave up and it looks kind of like this. Now, it doesn't have to be this whole thing. It could be just half of this. You might just see the increasing part. You might just see the decreasing part. But this is sort of like the stereotypical concave up portion of curve. What I want you to notice, though, if I just sort of sketch a bunch of slopes as x increases, those tangent line slopes are also increasing, right? So I sort of just pick 3 of them, but you'll notice that the slopes go from -3 to 0 to 3. And as long as this is a pattern along the entire stretch of curve that you're looking at, then we would consider that curve to be concave up. All right, so the portion of curve where the derivatives are increasing. An equivalent way of saying that is f prime is increasing. An equivalent way of saying f prime is increasing is f double prime is positive, right? F double prime is the derivative of f prime. And if f prime is increasing, then that means its slopes are positive. So f double prime would also be positive. So keep that in mind. These two are equivalent. Similarly, concave down, that's a stretch of curve or a portion of curve where the derivative values are decreasing. So this might be an example of a concave down portion of curve. Again, you might not necessarily see the whole thing. You might just see the left half or the right half. But this is, again, sort of just like a stereotypical portion of concave down curve. And with the 3 points that I chose, you'll notice that the slopes go from +3 to 0 to -3. So that's just illustrating that the slopes themselves are in a decreasing pattern. And if a portion of curve has slopes that are in a decreasing pattern, we consider that curve to be concave down. Equivalently, that means f prime, the slopes are decreasing. Or in other words, f double prime is negative. Okay, and these are equivalent. Now, an inflection point. The definition of an inflection point is a point on f at which there is a change in concavity. So now a lot of you have been thinking, okay, all I need to do is find where f double prime is equal to 0 or where f double prime is undefined. That's only partially correct because those values that you're finding are just candidates, right? So candidates for inflection points are points where f prime double prime is 0 or undefined, because those are candidates because at those points, or just around those points to the left of f, to the left and to the right of where the second derivative is equal to 0, there could be a change in concavity. So if f double prime goes from positive to 0 to negative, then that implies a change in concavity. Or if the other way around happens, that implies a change in concavity. These values where f double prime is 0 or undefined, that's just sort of locating where that could happen. All right. So once you identify the candidates, you then must go on and check the concavity on either side of those points to ensure that there is actually a change in concavity before you call it an inflection point. All right, so now going on to the question at hand. Let's read it. So C says, find all the values of x on that interval for which the graph G has a point of inflection. All right, so since we're looking for a point of inflection, that means I'm either going to analyze the first derivative or the second derivative, right? Because we determined here and here that I can identify a change in concavity, or I can identify concavity by looking at f prime or at f double prime. It turns out here that in this case we have the derivative function. So I wrote the derivative function right here. And so we're going to have to use the derivative function to identify concavity. So when does concavity change? Well, that question is equivalent to saying, when does g prime of x change from increasing to decreasing or vice versa, right? Because we said that if f prime is increasing, or if the derivative is increasing, then that's a concave up curve. If the derivative is decreasing, then that's a concave down curve. So to ask when there's a change in concavity is to ask, when does the derivative change from increasing to decreasing or vice versa? But that's also equivalent to, when does g double prime change from positive to negative or vice versa? Now we have to deal with what we're given, and we were given the derivative function. And so the derivative function is equal to 2 plus f of x. Really, this is the important thing because we have the graph of f of x. Now, it's true, g prime of x is not exactly equal to f of x, but it's equal to the function f of x and some vertical shift. So if I can imagine the f of x function shifted up 2 units, that would give me the graph of g prime of x. But since there's a vertical shift, and really since all I'm caring about is when is f changing from increasing to decreasing, I could really just use the graph of f, because shifting this graph vertically in any direction, like up or down, it's not going to change the intervals on which f is increasing or decreasing. All right, so from -4 to 0, you can see that as x increases, y is increasing as well. So f is increasing. In other words, that means g prime is increasing. All right, so that means on this interval from -4 to 0, g is concave up because its derivative is increasing. Similarly, on this side of the graph, f is decreasing, which is equivalent in this situation to say that g prime is decreasing. And if G prime is decreasing, that means that G is concave down. So there is a change in concavity right over here at x equals 0. And so the way we would argue that is we would say that G of x has an inflection point at x equals 0 because G prime changes from increasing to decreasing at this point. Notice I did not use the second derivative because we were not explicitly given the second derivative. So when I do argue for something like an inflection point, I want to argue using the explicit information. And in this case, the explicit information was the derivative of G and not the second derivative. So that's why I argued using G prime. All right. Part D goes on to ask, find the average rate of change of f over this interval. So the average rate of change, let's use another color because this thing's getting a little messy. Let's use purple. Average rate of change over this interval from -4 to 3. So basically, when I see average rate of change, it means, all right, I'm going to go to my endpoints. I'm going to, or whatever points, the endpoints of the given interval. And I'm going to go ahead and connect those with a straight line. That's a secant line. And I'm going to find the slope of that line. That will give me the average rate of change of f in this case. So the slope of that line is just -2/7. Okay, then the question goes on to say that, let's read it together. The question goes on to say that there is no point in this interval such that f prime of c is equal to that average rate of change. So in other words, as we go on from x equals -4 to x equals -3, and let's say we just draw a whole bunch of tangent lines, nowhere are we going to have a situation where one of the tangent line slopes is equal to this secant line slope. And the mean value theorem says that as long as certain conditions are met, we can guarantee that there will be a tangent line slope equal to a secant line slope. But that obviously doesn't happen here. And why is that? Well, the reason is that at this point right here, this corner, f is not differentiable. At that point, and that's at x equals 0. And one of the requirements for the mean value theorem to work is that your function is differentiable on that interval. So we would say that the mean value theorem does not apply here because f of x is not differentiable on the interval. Actually, I should say is not differentiable at x equals 0 on the interval from -4 to 3. Okay, so I went through that quickly because you can pause, rewind if you need, but I hope that sort of cleared up any confusion. I'm going to now go through and read the other questions from problem 2. And I'm going to try to answer them myself, like by typing. If I can't do that, then I'll make a video. But folks, I do have 2 daily SGI sessions, and I will say that yesterday we had some pretty successful sessions in that students came in, asked questions, and I was able to answer. And you can basically come in, ask a question, and then leave. You don't have to stick around. So I really highly recommend, thinking about coming to an SGI session. All right, ladies and gentlemen, I hope this helped. I will talk to you soon. Be well. Bye.